You know, it's kind of amazing when you stop and think about it, just how many tiny computers are, well, everywhere in our lives.
Absolutely everywhere.
I saw the statistic from 2020 that over 28 billion microcontrollers were shipped. Billion, with a B.
Wow.
Chances are, wherever you are right now, you're probably like only a few feet away from one.
It's a truly staggering number, isn't it? And it just shows how these embedded systems are, woven into everything we do, often completely unseen.
Right, working behind the scenes.
And what's really exciting, and kind of the point of our chat today, is how these devices are starting to merge with AI,
Mm.
artificial intelligence.
Exactly. And that brings us right to edge AI. That's our focus for this deep dive. It's that meeting point, the intersection of embedded devices and AI.
Mm-hmm.
You can think of these edge devices as, well, as the link between the digital world and the physical one.
Yeah.
They've got sensors, right, collecting all this data.
So much data.
Yeah.
Just constantly sensing their environment.
But here's the catch, and the material we looked at really highlights this.
Yeah, the bottleneck.
Precisely. You have this flood of data, but maybe the actual information content isn't always that high, or at least not all of it needs to be sent somewhere else immediately.
Right. You end up with this situation where devices collect way more than they can realistically transmit. Bandwidth is limited. Or maybe sending data just eats up too much battery.
So tons of potentially useful data just gets dropped or ignored.
Often, yes. Because sending everything back to, say, the cloud for processing just isn't practical or efficient.
Okay, so that's the problem Edge AI is aiming to solve then.
Right.
Bring the smarts, the analysis, directly to the device.
That's the core idea, exactly. Run the AI, the machine learning models, right there on the edge device itself.
Which means you can figure out what's important locally.
Mm-hmm. You extract the insights, the meaningful bits right at the source. Then you only need to send that relevant info, not the whole raw stream.
Makes sense. Much more efficient.
Way more efficient. Saves bandwidth, saves power, solves a lot of problems.
And that's pretty much what we're digging into today, focusing on the first chapter of the material we've been reviewing. It really lays the groundwork.
Yeah, it sets the stage nicely. We need to get the key definitions straight and understand the core benefits that make Edge AI so, well, compelling.
Perfect. So if anyone listening is wondering what Edge AI really is and why there's so much buzz, this is the place to start.
Definitely. So first things first, let's nail down some terms, like the chapter does. It starts with embedded systems.
Right. We mentioned them already, but the key idea is they're dedicated, yeah.
Yeah.
Built for a specific job.
Exactly. Unlike, say, your laptop or phone, which can do almost anything, an embedded system is designed for a single task, or maybe a small set of related tasks.
Like the example on the text, a digital watch. Its main job is just telling time. Pretty straightforward.
Very straightforward. Or a slightly more complex example they give is a smart TV. It runs embedded Linux. It's more capable, but it's still fundamentally about, displaying media, handling apps related to that.
Still focused, not a general purpose computer you'd write code on or something.
Precisely. That dedicated nature is key. Okay, so building on that, we get to Edge AI.
Which is just putting AI onto those edge devices, right? Simple combination.
At its core, yes, edge devices plus AI. But then the chapter introduces two related terms we should probably clarify. First is embedded machine learning, embedded ML.
Okay, so embedded ML, that sounds like the broader category, just running ML models on any embedded system.
You got it. It's the general practice of putting machine learning onto these specialized hardware platforms.
Gotcha. And the other one was tiny ML, tiny machine learning, and they made a point of the little registered trademark symbol there.
Yes, the O. That's important. TinyML is a specific subset of embedded ML. It focuses on running machine learning on the most resource-constrained hardware you can imagine.
Like really tiny.
Really tiny. We're talking about microcontrollers that use incredibly low power, maybe some DSPs, or those little FPGAs, field programmable gate arrays. The absolute low end in terms of power, memory, and processing capability.
Wow, so it's like the extreme sport of embedded ML, trying to squeeze AI onto the smallest, most efficient chips possible.
That's a great way to put it. It really pushes the boundaries of efficiency. Doing useful AI with, maybe only kilobytes of memory and milliwatts of power.
Okay, that distinction makes sense. So embedded ML is general, tiny ML is the super constrained end. Cool. Then the chapter jumps into the why do this, and it introduces that acronym, BLER-P.
Yes, GLER-P. It's quite memorable, isn't it? It comes from Jeff Beer, who founded the Edge AI and Vision Alliance. It's just a handy way to remember the main advantages.
Okay, let's unpack BLURP. That's bandwidth, right?
Correct. Bandwidth. We touched on this already. IoT devices, sensors. They can generate just a massive amount of data, often far more than the network connection can handle, or more than makes sense to send from a power perspective.
Like trying to drink from a fire hose, basically.
Pretty much. And a lot of potentially valuable stuff just gets dropped on the floor
Yeah.
because you can't send it all. And remember, network communication. That's often the biggest power drain on these little devices.
Right, sending data costs energy.
A lot of energy.
Hmm.
So Edge AI steps in,
Hmm.
analyze the data locally. The text gives that example of an industrial machine with a vibration sensor.
Yeah, I like that one. Instead of streaming vibration data constantly.
Exactly. The device itself analyzes the patterns. Is everything normal? Fine, don't send anything. But if it detects an anomaly, like weird vibrations that could mean a failure is coming,
Then it sends an alert. Just the alert.
just the alert, or maybe a small snippet of the relevant data. It's a huge reduction in the amount of data transmitted.
Massive difference. Saves bandwidth, saves power. Makes total sense. Okay, so B is bandwidth. What's L?
L stands for latency.
Ah, delay, the time lag. This seems obviously important for anything real time.
Absolutely critical. Latency is the time it takes from when something happens in the physical world to when the system responds.
Mm.
If you have to send data to the cloud, wait for processing, and get a result back, that takes time.
Too much time for some things, like an autonomous car needing to brake now.
Precisely. Or a factory robot needing immediate feedback. You can't afford the round-trip delay to the cloud in those cases. It could be hundreds of milliseconds, maybe even seconds, depending on the network.
But with Edge AI, the thinking happens right there.
Right on the device. So the response can be almost instantaneous. It dramatically cuts down that latency.
Okay, crucial for real-time control. Makes sense. So BLE is next. Economics.
Economics, yes. This is about the cost savings.
How does it save money? Less data transmission, I guess.
That's a big part of it. If you're sending way less data, you might need less expensive data plans or less robust network infrastructure. Think cellular data, costs for thousands of devices.
Okay, that's up.
And also, potentially less reliance on cloud computing resources. If the edge device is doing more of the heavy lifting, you might not need as much powerful processing or storage in the cloud.
So lower operational costs.
Yeah.
Both for connectivity and potentially for cloud services.
Got it. BLER must be
Reliability.
reliability. How does running AI locally make a device more reliable? Well, think about what happens if the network connection goes down. If your device relies entirely on the cloud for its intelligence,
It becomes dumb brick.
pretty much, yeah, it can't function as intended. But if the intelligence, the AI model, is running locally,
It keeps working, even with no internet.
exactly, it can continue sensing, analyzing, and making decisions based on its local processing, regardless of network status. This is huge for critical applications or devices in remote areas where connectivity might be spotty.
Like that self-driving car again. It can't just stop working if it hits a tunnel and loses signal.
Definitely not. Or think about a remote environmental sensor. It needs to keep operating even if the network link is temporarily down. Edge AI provides that robustness.
Increased uptime, basically. Okay, makes sense. Last one, P.
P is for privacy, and this is a really big one today.
I can see why if the data stays on the device.
And sensitive information doesn't necessarily need to be sent to the cloud or some third-party server. The analysis happens locally.
So take a smart security camera example. If it analyzes video on the camera itself to detect motion or people.
It only needs to send you an alert, maybe a short clip, when something actually happens.
Right.
A raw footage, potentially hours of it, showing the inside of your home, doesn't have to leave your local network.
That feels much more secure. Less chance of data breaches or misuse if the raw data isn't flying around the internet.
Precisely. It enables privacy-preserving applications. Think healthcare devices processing sensitive patient data, or even industrial systems analyzing proprietary operational data. Keeping it local is often much safer.
Okay, so BLRP. Bandwidth, latency, economics, reliability, privacy. That's a really solid framework for understanding the core benefits.
It really is. It helps you evaluate, is Edge AI the right tool for this particular job, given these potential advantages?
Now, the chapter then shifts gears a bit, talking about performance, and it introduces this idea of good enough versus always aiming for the absolute best accuracy.
Yeah, this is a key mindset shift compared to a lot of traditional AI research and deployment, especially cloud-based stuff.
Where the goal is often like squeeze out every last fraction of a % of accuracy, right?
Oh.
Using massive models, tons of computing power.
Exactly. Giant models, sometimes gigabytes in size, running on powerful GPUs. That's just not going to happen on a tiny microcontroller running on a coin cell battery.
Right, the resources just aren't there, so you have to be more pragmatic.
Totally pragmatic. The goal shifts. It's not about achieving the absolute best theoretical accuracy. It's about achieving performance that is good enough for the specific task while staying within the very strict power, memory, and compute budgets of the hardware.
So a slightly less accurate model that actually runs on the device is way more useful than a perfect model that can't be deployed.
Absolutely. The text mentions, for some simple tasks, a model might only need a few kilobytes of memory,
Mhm.
which is amazing. But for complex things like image processing, yeah, you'll need more sophisticated models, but still optimized for efficiency. It's a balancing act.
Finding that sweet spot between capability and constraint.
That's the name of the game in Edge AI and especially TinyML.
Okay. And speaking of constraints, the hardware itself. The chapter points out this is a big challenge. There are just so many different types of embedded hardware.
Oh, yeah.
Yeah.
It's described as a huge diversity. Countless chips, boards, development kits from tons of different manufacturers.
And they all have their own tools, their own ways of being programmed, their own quirks.
Exactly.
Yeah.
It can be,
Wow.
well, a bit of a jungle for developers. On the one hand, this variety is great because it means there's probably a perfect chip for almost any application you can dream up.
But on the other hand, choosing the right one sounds kind of daunting.
It definitely can be. You have to weigh up performance, power consumption, memory, cost, what sensors or interfaces it supports.
Yeah.
It's complex.
The text does say they'll get more into hardware selection later, which is good because it seems pretty fundamental.
It is absolutely fundamental. The hardware choice dictates so much about what's possible.
Right. And then the chapter wraps up by touching on some common use cases, kind of bringing it back to where Edge AI shines.
Yeah, it reiterates that it's especially valuable for devices with lots of sensor data, but maybe limited compute or, crucially, limited connectivity,
Ooh.
which turns out to be a lot of devices.
And even if you do have good power and network, those bill or P benefits still often apply, right? You might still want lower latency, better reliability, privacy.
Exactly. Portability often means strict power limits. Reliability is often key regardless of network. Privacy is increasingly important. Cost is always a factor. So even mains-powered, well-connected devices can benefit.
The example they use is a simple fitness tracker. It might have an accelerometer sampling really fast, capturing loads of movement detail.
Tons of detail. But if it tried to send all that raw accelerometer data over Bluetooth constantly,
Your battery would die in like an hour.
probably, yeah. It's just too much data, too much power drain.
Yeah.
But if it processes that data on the tracker itself to count steps or figure out if you're running or cycling,
Then it only needs to send the results. Steps. 10,000. Activity. Running. Much less data.
way less data, way less power. It makes the whole concept feasible. It allows the device to actually work as intended.
So it's about smart processing at the source, optimizing the whole system.
Precisely. From sensor to insight, making it efficient and effective within the constraints.
Okay, so let's maybe quickly recap this first chapter. We've defined edge AI intelligence on embedded devices. We've got the Beeler-Appy benefits: bandwidth, latency, economics, reliability, privacy.
We've talked about that crucial, good enough performance mindset, adapting to resource constraints rather than just maxing out accuracy.
And we acknowledge the challenge, but also the opportunity presented by the huge diversity of embedded hardware out there.
Fundamentally, it's about unlocking insights from data right where it's generated, getting around the limitations of sending everything back somewhere else.
Bringing the intelligence closer to the action, as you said.
Exactly. And this chapter really just sets the table. The material hints at what's coming, diving deeper into the specific hardware, the algorithms, how you actually build data sets for these devices, and looking at more real-world examples.
Yeah, it feels like we've just covered the what's and why, and now the how is still to come. Lots more to explore.
Definitely a lot more ground to cover. It's a rapidly evolving field.
So maybe a final thought to leave listeners with, building on this.
Yeah, how about this? Just take a moment and think about all the raw sensor data being generated right now, all around you. Your phone, maybe a smartwatch, smart speakers, traffic sensors, equipment in factories, just countless devices sensing the world.
It's probably an unimaginable amount of data globally.
Exactly. Now consider how much of that raw data is essentially being wasted or just not used to its full potential because it's too difficult, too costly, or too slow to analyze it centrally. How many insights are we missing?
How many problems could we solve earlier, or processes could we optimize if that analysis was happening right there at the edge?
Right. Think about everyday things. Could your appliances be smarter, more efficient? Could traffic flow better? Could potential failures be predicted sooner? Where could putting intelligence closer to the data source make a real difference? So, well, it's a pretty exciting space to think about.